How are we doing today? All right, let's go. So this is going to be a beginner-friendly, but a developer talk, okay? So it's still going to be technical enough. What he said, what's happening right now in the world? You're seeing these AI models are getting smarter, right? So you're saying, hey, what's going on? Now, the way you look at this chart is on here is MMLU. How many of you know what MMLU is? Okay. It's a benchmark. It's a benchmark that's used to evaluate how smart, like think of it like an SAT or some, SAT is American. Think of it like it's just a test with multiple choice questions. It has like thousands of multiple choice questions. It's like over 15,000, I think, so it's a lot. And then like if I was to take it, it would take me, I don't know, a month to go through every question, right? And it was designed by researchers at OpenAI and Berkeley. And so that's how you evaluate. It's got like science, math, and all that kind of stuff, but it also has humanities, social studies. So it's a very comprehensive benchmark, so a lot of people like using it. But the thing I want you to take away from here is that when you have humans take that test, that's the line that they score, human expert. What we're seeing now over time, right, pre-2022 until now with DeepSeek and OpenAI models, is you're seeing that they're starting to meet and surpass. So the question, we're gonna talk about two questions today. One question is, why does this happen? Why do they keep getting smarter? And so I'm gonna talk about scaling laws. And then we have the number two question is gonna be about what do you do about it? How do you use it? So let's just get started with question number one. Our goal as an application developer, my goal is to use the model, not always to train the model, but I need to know a little bit of how this model is trained. If you guys drive a car, how many of you know what internal combustion is? How many of you know what an electric car is? How many know what a hybrid engine? You don't need to know exactly how it works, but you need to kind of understand it because as your driver, the braking and a little different, right? So that's what we're going to do today. We're going to just understand it at a level that says, okay, that's what it is. So let's, I forgot to say something. So now, I did get that. All right, so let's talk about training. So there's two eras of training. There's the pre-transformer era and the transformer era. So the way we did it in the pre-transformer era is you have a whole lot of humans go and say, hey, computer vision was very popular. So you'll have a lot of pictures of cats or cars or whatever, and it was all labeled. And so you take the labeled data, you separate it out, you separate the label, you separate out the data, and then you'd start with a model. There's a model architecture. We won't get into the details of that, but different model architectures learn different things. There's a whole bunch of parameters there. And so you get the model to guess the label. What is this image? And then you compare that to the actual label, and then you backpropagate. Right? So backpropagation is you go back. So you think of the model as like a machine with a whole lot of knobs. And I say a whole lot, I'm talking billions of knobs. Okay, you just can't imagine billions, but billions. And so you go and you tweak them every time. And then over time, as you do this over and over and over again, you have a trained model that when you give it data that it hasn't seen before, it starts guessing the correct label. Okay? Pre-transformer era, that was very cool. That's how we did things. But so models would get faster, and these models, we came up with more data. The more data we add, model would get faster. The more compute we had to add, the bigger the model size. You can see model size went up as well, like the amount of parameters that were there. So intelligence got up there. But we were limited. We were limited by human label data, right? That was the thing. We couldn't have enough human label data. We had researchers working on all sorts of different ways to start labeling data automatically and things like that. But something pretty cool happened is we have the transformer architecture. And so the transformer architecture is a completely different architecture that lets you train, it's the ability to train from unlabeled data. So I no longer need to have a whole bunch of humans labeling these things. I'm able to use unlabeled data. So I'm going to explain to you just a little bit of how this works. But because I can train from unlabeled data, and it started with text, I can take text, a lot of text. We had something called the internet that has a lot of text and a lot of information. And so I was like, wait a minute, I could start training, like the models today are pretty much trained on the entire internet. Pretty much, right? There's a lot of private data they're not, but that's kind of how it works. So how does that work? So you take this unlabeled text data. And what I do is, there's a interesting, I don't actually use the words. In the world of transformers, there's this thing called a token. How many of you can token, So when you think of a token, you think it's like this little thing. But a token is actually a vector of thousands of numbers, thousands of dimensions, and the amount of the size of that token or the number of variables there is dependent on the model. Like GPT has a different set, this guy's have a different. So, and a token, for the purpose of this talk, a token is a word. Just use it as a word, but it's not actually a word, because if you have a word like misunderstanding, it's 3 tokens. Misunderstanding, it's 3 tokens. That's how these models work. Okay? If you want to learn that, I'm sure you can find a whole bunch of stuff on YouTube explaining this kind of things. But you start there, you convert it into tokens. And then you take those tokens, and now you have tokens in sequence, right? I know what token n is, I know what n plus 1, n plus 2, n plus 3. So now this architecture, you train it by giving it a token, and you say, hey, what's my next token? And then you get it to guess that. But I already know what the next token is. So you do that, and this is way more computationally, it uses more computation to do this, but models are getting smarter, right? And then after you keep doing that lot, and these models are bigger too. These are the GPTs, the trillions. We have even like there's speculation about over a trillion parameter models, some private models and things like that, but these are massive models. So that's how they're pre-trained. So these are pre-trained, but the thing that they're done is they're pre-trained without ever seeing any human labeled data, right? It's never seen human labeled data. The only thing it's done is it's kind of seen everything that you've shown it off the internet or something like that. So what it does is it starts, going back a second, but what that did is that started improving the intelligence, because now I'm not limited by human labeled data, right? This just in our industry and technology, like life kind of goes, like you get this wave where things are going amazing, and then you kind of cap off, and you get new technology, and it kind of this S-curve kind of pattern. So this is what you'll see throughout some of the things I'll talk about. But what I was going to say is, so that's pre-training scaling. Keep adding scaling there. But because it's never seen any other data, like any of the labeled data, usually you have to take these pre-trained models. You don't really use them in your application right away. You can, they're just not that great. Like to turn it into a chatbot, it has to be done. These are a couple of techniques. There's lots of different techniques for post-training, but Transformers created this era of post-training, where you take a pre-trained model and then you post-train it. You go and you can teach it how to use tools like, hey, go on the internet and do some searching. You can the supervised fine-tuning is I can turn it into instruction tuning is a very popular supervised fine-tuning thing, where you say, you take a pre-trained model and then you teach it how to be a chatbot. You show it like question, answer, and it starts learning how to be a chatbot. So by pre-training it, you gave it a general understanding of the structure of language. And remember I talked about tokens? So tokens aren't just text. Tokens can be audio, video, radar signals, molecules. So we're figuring out how to turn pretty much anything into tokens. And then you use this AI model to now predict the next token. So lots of applications for it, again, and being able to be used in kind of pretty much so many different applications. All right? So, and then let me talk a little bit about how supervised fine-tuning works. Very similar to what we talked about earlier, where you have, like remember the original diagram where we say you gotta do the classical, I guess, the back property, you do the exact kind of same thing. But now that I have a pre-trained model, the difference that you see is, let's see this work. There you go. Oh, no one can see that. No one can see that, right? All right, the pre-trained model is the difference, right? I'm not starting with random weights. I'm starting with a pre-trained model. It's like having like I said, something that understands our language, understands some basic structure of the things that's been seen. And now I go and I fine-tune it with the label data, something specific that I want, like I said, the instruction tuning, where I want to turn it into a chatbot, and then it'll start doing it. So if you noticed, when I went to the transformer pre-training, there was no Y. I can go back inside. Now I reintroduce the Y element where I have a label, right? Another very popular post-training thing is reinforcement learning from human feedback. Have anybody probably seen that anywhere? No. So there you go. I see a couple of hands, but I see more hands. So this is good. I'm glad you guys are hopefully learning some of this stuff. So when you see it in the future, like, oh, I know what that is. So reinforcement learning, human feedback is a technique that is about preference. So what that means is, as a human, like when I did the chatbot example, I took a pre-trained model, I gave it a bunch of question answers, and then it created answers. So as it's creating these answers, if I give it, and these systems are not deterministic. So for the question, I may get a different answer than somebody else prompting it and somebody else prompting. So you get different answers and you get different things. So what you do is you take the same question, you get two different outputs, or multiple different outputs usually. And then you have humans who will look at it and say, I like this answer better than that answer, right? So that's a lot of work. And we did a lot of work. And it's actually not just, I like this one better than that one. It's also like, well, this one is more racist, or this one is more friendly, or this one is, so like there's lots of parameters about it. So human preference is actually a big thing on its own just to create that. What kind of questions do you ask? How helpful is it? But then you create this database, and that's kind of expensive. So you get all this human labeled data again. But now you're labeling the response, right? So now with that, I create what's called a reward model, which is, again, you go train a whole new model. So pattern you'll see is I'm doing a whole lot of things with trying to get the AI and the model to do things and do it automatically and do it by itself. The reward model is a model that when you give it a question, it tells you what the score would be, right? And so you use that. So now you have a model instead of all this human stuff, and you use that to go fine-tune the model. So then you go back and you go do these things like, okay, you want to make this model be more kinder, or you want to make this model be more safe and not talk about certain things. So you can start fine-tuning it, or you want to make it more friendly, or you want to make it be a lot more aggressive or whatever, right? So they got these types of things to kind of fine-tune that model in a way that the chatbot has a certain characteristic or behavior that we think humans will prefer, right? So that was what reinforcement learning human feedback. Now, but we had the same problem again, is I had to go get a whole lot of human preference data. So the answer was actually, to get past this hurdle, the answer was actually already with us, is what we did was we said, hey, wait a minute, if I have this model that is trained to predict human preference, I can start doing this immediate loop, where I say, okay, I give it a prompt, I use the post-trained model, I get a response, I get human data, and then immediately go back and adjust the weights, and I try again. Because you notice what we did before, so it's a subtle difference here. So what we did before is we do it offline, and then we train this model, and then we test it out. We do it offline, train this model, test it out. Now we're in the loop. So you can imagine, with the things I told you in post-training, is where a lot of the work right now is. So you pre-train this big model, and then you spend a lot of time post-training. So post-training compute is a huge thing. And so what you're seeing, because of post-training, and then the transformer era introducing post-training, you're seeing that so the other thing that's tricky here is that this scale is actually logarithmic. Not logarithmic, sorry, exponential. 23, 24, 20, so it's 10 to the 26. So this is, that line, you wouldn't be able to draw it on the screen, right? But this is the evidence of what I've been talking about. You're seeing how pre-training moving to post-training, and compute, as compute goes, you're using more and more compute, it's improving these models. Okay, so as you're investing in post-training, you're getting these models to be smarter, you're getting them to be more useful. And these are all things that are happening. And Chris mentioned it earlier, is that, oh my gosh, you're thinking, all this compute, how's the power, the costs and stuff? So at NVIDIA, we're working very hard on trying to keep that under control, right? So this is just an example of what's happened in the last 10 years. If you're to train GPT-4, which was a very large model, in 2014, it would have taken over 5,000 gigawatt hours, whereas in Blackwell, it's 3 gigawatts, and it's going to be even less. It's 2 point something for Blackwell Ultra. So we keep pushing that down. So you can do all this great work using a lot less power, but you get more compute, more capability. Okay, let's talk about. So those are two. So now what you do in your application, you just use a post-trained model. That's what a lot of people have been doing for a little while, where a lot of excitement was, where you just use the ChatGPT interface or something like that, the API, you're using just the API interface. You're using these post-trained models. But the way that works is, in your application, you send it a prompt, and you get back a response. And the responses are good For every prompt, you get back a response. What's happened recently is all these models started reasoning, or it's like, so that's another technique. It's actually a type of reinforcement. You use RLHF to post-train the model to be able to learn how to reason. So you start showing it things that says, this is for this math problem, this is how you reason it out, this is what the answer is, and then you train it to reason. And reasoning is really just at inference time. So reasoning is also sometimes called test time scaling, or sometimes called inference time compute, or inference time scaling. So there's these different names, but it's quite simple. What it is the model itself, instead of me, the human, prompting the model, and then I get an answer, I give it one prompt, and then the model prompts itself. It goes, hey, wait, do I have the right answer? Did I do my double checking? Can I fact check it? I mean, when you're doing this, if I put you in an exam, and you're going through and you're answering, questions about the history of Berlin, you're going to say, wait a minute, was it like that? Can I double check this? Was this the right date? The model starts doing that, and it starts asking itself these questions. So the answers, you can imagine, are going to be much better, higher quality. So that's our third law, and that's how the three... let me show you how the reasoning works. So this is a sample application. I'll show it to you again, and you'll get the application for it. But what you want to pay attention to here is at some point we put the prompt, and as it's generating the answer, look at what it's saying. Try to read some of that text. The video is a little fast, but try to read some of that text so you'll get an understanding of what a reasoning model, what it's doing, what does that thinking look like, okay? So this is where he's taking the prompt and putting it into the model. Model thinking. And that's how we have our three scaling laws: pre-training scaling, post-training scaling, and test time scaling. So you're seeing more and more compute is leading to more intelligent models. So that's my kind of, how are these models getting faster? And so even with training, people are like, oh, the cost of training is going up so much. With inference, we're also doing the same work, right? We're optimizing inference, and we're reducing the cost of inference. We're reducing the cost per token. And with the latest Blackwell Ultra, it's like we've gone down to 2 joules per token. So it used to be, imagine for generating a single token, it could have taken 42,000 joules for that, because it's such a big computational workload. But we've been optimizing the software, the hardware, creating the full system in order to reduce the cost so you can keep doing tokens. And so these costs will keep pushing them down as we get more efficient. We'll keep pushing on that. All right. So that was for you to understand electric car, gasoline engines, get all that, right? So you kind of understand what you're playing with. But as an application developer, that's who I think a lot of, right? If you're training models, yeah, come talk to me and I'll be happy to talk to you. But I'm going to talk about application developers who are trying to use these models. Because honestly, my thesis right now is that, this is a famous tweet from Andrej Karpathy. Some of you guys might have seen this, right? The hottest new programming language is English. And last year when I was here, I kind of showed you this kind of thing where I had a function that was doing sentiment analysis. It was pure Python. And I said, now with the world of AI and with these language models, I can start asking it in English how to do this. So my thesis is, as an app developer, I don't need to go train these models. Here's what my workflow should look like, right? I'm just going to start with an API endpoint somewhere. And we have those at NVIDIA if you want to try them out. Build.nvidia.com. Just go to your browser. You can get a free account, and it gives you a rate-limited API as a developer. You can go use it. But you start there, and then prompt engineering. You hear this term prompt engineering. That's writing very structured English. Give it context. Give it a role. Tell it exactly what you want. Tell it exactly what you don't want. And that takes a lot of effort to think through that. And the same mindset that you have as a developer that's very structured and can think about these things, you use that, but then you just articulate it in English instead of articulating it in Java, C++, Python, whatever, right? So you go do that. There's a whole bunch of model evaluation tools. I'll explain that to you. You'll prototype your application. You'll decide which model to use. And then you can, you have to, I'm going to recommend you implement guardrails, and I'll show you why. And then you go get customer feedback, and you can do that loop, and you go to a production application. You may never need to go get custom data and fine-tune your own model. May never need to. Some cases you might, because your application might be so narrow in a certain area. These models are so capable, right? You're getting this amazing capability. It's superhuman, super intelligence is a word people are using now. And you're getting this capability that you can just use it, right? All right, so a couple of things. Questions I get asked a lot is like, hey, there are open models and they're versus proprietary, right? There's open weight models versus proprietary models. What should I use? I say, why choose? Just use both. I mean, now what's happened, that's what this trend graph is. This is another benchmark. Artificial analysis kind of takes MMLU and a whole bunch of other evaluation benchmarks and makes some aggregate score. But what you're seeing here is that the capabilities the gap is closing. The proprietary models were ahead. Open source models have been continuing to catch up. The gap is closing. So depending on your use case, right? If you need to have a model that you need to run locally on something, go get an open model and it'll be great. If you need to use ChatGPT or other endpoints or whatever, just use those. They're fine. Great. Build.nvidia.com gives you endpoints so you can try it. So go figure that out. It's just an API. So the other thing that I get asked a lot is I get asked about reasoning models. Like, hey, should I be using a reasoning model? And I mean, the data is kind of obvious. So that, again, that number is similar to that number I showed you in the chart before. You'll see some NVIDIA models. You see the private models. You see open models. And my answer now is just you should always use the reasoning models. Right? Yes, they cost more compute, but we're pushing the cost of compute down. We're pushing the energy of compute down, but you're going to get a higher quality answer. This is one of those things where if the answer to a question, it's I say, what's 10 times 10? The answer is 90. And it's like, well, no, it's not, but it cost me a whole lot less compute, and it was, not a reasoning model, but the answer is 90. It's useless. It doesn't matter. The reasoning model will get you will tell you the answer is 100. The other model might. This is a dummy example, but that's the kind of thing you're doing. Is that incremental accuracy is not, which actually gets me to my next point. Is the benchmarks aren't the end all be all. If you look at these benchmarks and you say, oh, that's the best model, so I have to use that, or that's the best model, I have to use that. Not enough. There are lots and lots of benchmarks out there. I don't expect you to know all these, but this is just how we categorize them. We actually have a tool to help you with that called Nemo Evaluator. But these, like for large language models, there's a set of benchmarks for that. For vision language models, there are different benchmarks for that. For reasoning models, there are different benchmarks. You can and should look at the benchmark data. You can and should use that or use the tools to kind of evaluate some of it and decide what's going to be useful for your application. But that's not going to determine the accuracy of the answers on your application. You have to test it in context in your application, right? So benchmark performance is not application performance. So please, that's my kind of takeaway on the benchmarks. It's a leading indicator. It's not a guarantee. So the other, this is the fun one. So when I talk about guardrailing, so you can look at this example. Give me a second. This is what your application has to worry about now. You have to worry about this. This is, if you notice, like this is what an attack on your application could look like, right? Because now you have this LLM, non-deterministic system, and if you keep like attacking it and keep saying, no, you're wrong, I'm right, and because they've been trained to please you, which we talked about with RLHF and all that, they're gonna want to kind of say, agree with you, and if you've seen these things on the internet where if somebody pushed it hard enough, you can ask it to tell you how to make a bomb or something, and so you don't want those things, right? So I am Canadian, by the way, so that was actual real test. That was a real test. It was a real answer. Okay, so it was not made up. But this is where you have to get very precise and very specific. So system prompts, guardrails, and guard models. Those things help you improve your application. So you should use them. We got Nemo guardrails to help you with that. But there are lots of things out there, and this is what a system prompt. So this is a guard system prompt. I'm using that as an example. So you'd put this. And you can see how detailed it is. So this is for a banking application. I don't want my banking application to start giving stock advice, to start telling it to buy this or sell that. I want my banking application to help my user with very specific transactions, right, with their bank balance or those types of things. So I have to tell it exactly that. Even there, people will keep attacking it, try to say, oh, and they'll figure out. So what's interesting is that this attack point isn't the same anymore, right? So security in the context of AI applications has come to a lot more, social engineering. The question is, I bet if you search the internet for gaslighting and LLMs, I'm sure you can find lots of things about either using the LLM to gaslight, and now you have an LLM that'll attack the other LLM. So this is getting very interesting and challenging. But the other one I want to make sure you understand is there's guard models. So you can go and, for example, if you use Llama as your model, they also have Llama Guard. So you can use those guard models, which they have already created and helped it have the guardrails and things. So you put that in your application so that it can guard against attacks as best you can. So use guardrails. Don't ship applications without guardrails. All right. This is what you looked at before. It was a data analysis agent. So the reason I didn't show this first is because agents is what a lot of people are talking about now, and it's like everyone wants to build an agentic application. So what exactly is an agentic application? Like as developers, you've been building modular architectures, and you think about building modular architectures, right? Agents is kind of the same thing. Use that same mental model for yourself to say, okay, how can I something I would put into a modular architecture is now going to be an agent, right? So this application that you saw took the Titanic data, and then you can ask it questions, and it would do some analysis like the charts, and it would do things. And the way it's architected, it has a data frame, a data insight agent, and each agent uses tools, right? So this is the architecture, and if you go to that URL, you can look at the whole code. It's all Python. This is where I said this. Let me show you one other fun thing. This is what the code for the tool looks like. This is actually just copied over from the GitHub. You notice how much English is in there. The tool, like that's how you define the tool. It's a prompt, right? So if you go back, so you have all these tools and stuff. So go look at the code. You'll see that what actually happened with this code is about 25% of it is English, and then 75% of it is Python, actually. So it's not 100% English. So don't freak out too much. If you're building these things, actually, I've got a couple of things to close out here. Is that we have if you're building on Google Cloud, we have a developer community that we just created where you can go and you can learn how to build these things with using NVIDIA technology, using Google technology, and on this community, we're about to launch very soon. We're going to be launching a joint learning path, probably by the time you get home, who knows. And you can go sign up there. That's the URL. If you want to learn more, we have a whole bunch of free self-paced DLI courses. You can grab a free course by using that. There are courses like getting started with deep learning. There's real-time video, AI, and then there's things about deploying models at inference. So you can try that stuff out. So 2 things we talked about. We talked about how these AI models are getting smarter. You understand the engine of the car you're kind of driving, and then my statement about the modern AI application workflow is you start and you build these applications like this. Okay. So if you want to talk to us more, we're down at A16. You can come meet us there. And also, we love celebrating our developers. And so we have a wall and things, so you can take a selfie, tell us what you love about what have you built, what are you proud about building, and we'll put it up on the wall. So that's it.